I think I need to tell you some more calculus. I mean, there's two ways I can go here. I can do some examples, one-dimensional physics and things like is in my lecture 16. Maybe I'll do that at the end of class. But I think it's just more logically oriented. If I just kind of go on with the calculus 3 story, tell you the next major thing, and then besiege you with examples after that. Yeah.
Are we going to talk about centrifugal force?
Not really.
Okay, so we did have a question in the website homework about it.
Yeah.
Will there be questions about it on the test, do you think?
Well, that'd be quick. I mean, it's possible. We have talked about the centripetal acceleration earlier. Centripetal force is tied to that, but I'll talk about that some other day if you ask me again.
All right.
Sure. So, other questions? Reasonable questions? I'm just ignoring it. Other questions?
Why the Band-Aid?
Oh, well, I was watching the Oscars and I was inspired. I should start something. Soon you'll all be doing it, like by next week. Minion Butcher. Okay.
That means it was an embarrassing story he doesn't want to share.
Nothing that exciting.
Did you get bit by a vampire?
Did I get bit by a vampire? That's my knowledge. So I'm going to talk to you guys about conservative forces. Conservative forces. Or I guess you could say conservative force fields if you wanted to. To do this properly, I need to tell you a little bit more about calculus 3 that you might not already know. In particular, I need to talk to you about partial differentiation. So let me just give you a crash course in partial differentiation. Partial differentiation. There we go. All right, so essentially, partial differentiation is just this. You differentiate. I can't spell differentiate today for some reason. Differentiate while holding the other Cartesian coordinates fixed. So in other words, you pretend like the other Cartesian coordinates are constants. For example, partial x of x squared plus 2xy. All right, so, and this is not a d, it's a funny looking script d, partial derivative, okay? So partial x of x squared, it has linearity, but then here's the thing, you can pull the y out. So the y is constant, you can pull it outside the derivative. So what's the derivative of x squared? It's just 2x. What's the derivative of 2x? It's 2. So you get 2y. Another example. Partial y of the sine of x, y, z. We can do partial differentiation with 2 variables. We can do partial differentiation when you've got 3 variables, x, y, and z. We do a little bit of 2-dimensional stuff in here and 3-dimensional to try to show you a little bit of both. But the basic rule for differentiation is the same as you've already learned. This is a composite function, right? I got to do the chain rule. So chain rule says differentiate the outside function with your sine. So I get what? Cosine of x, y, z. And then I take the partial derivative of the inside function with respect to y. So that's x, y, z. In this case, x and z are constant, right? So I can pull the x out and I can pull the z out in front because they're constants with respect to the partial differentiation. All right, that's basically the definition of partial differentiation, is that you treat the x and z like constants here. So I get x z cosine of x yz times partial y. Guess what partial y is? 1. Yeah, exactly. So this is just 1, and that's the answer. All right. Here, another example. Partial z of the exponential of x squared plus y squared plus z squared. How would that work? Chain rule again, right? So I do the exponential of the thing. And then I have to multiply by partial z of the argument of the exponential, which in this case was x squared plus y squared plus z squared. All right. Now, if we're differentiating with respect to z while holding x and y fixed, that means that x squared and y squared are the constants to this differentiation, right? So we simply have this is 0, and z differentiates to what? 2z. Yeah, 2z. So the answer here is 2z e to the x squared plus y squared plus z squared. All right. In other words, if you can differentiate, you can partial differentiate. It's not really that big a deal. You with me? Never no? Don't say no. I refuse to accept that no today. You guys can partial differentiate. Now, I will start to lose you guys with the next thing I'm going to introduce, which is called the gradient. So the gradient. So for a function of two variables, we have the gradient of f, or upside down triangle, nabla f as it's called. This is partial f, partial x, comma, partial f, partial y. So for a function of three variables, the gradient is a 3 vector. So you have gradient of f, partial f, partial x, partial f, partial y, partial f, partial z. The important point here is that the gradient, it takes in a scalar function, a function which is just real value, right? And it gives back to you a vector field, all right? It gives back to you a vector which you can assign to each point in the, say, space you're looking at, be it 2-dimensional or 3-dimensional. So the gradient is this, it's a bridge between worlds, the world of scalar functions and vector fields, all right? Vector fields represent forces. They're force fields. And we learned last time how to calculate the work done by a force field along a path, right? So now, just to give you an example, let's look at the gradient of something simple. How about here? Here's an example. How about nabla of x squared plus y squared? We'll think 2-dimensionally here to start with. So there you got yourself 2x, comma, 2y. Why is that? We'll put the work for this quality here. Partial x of x squared plus y squared is equal to y squared differentiates to 0, x squared differentiates to 2x. There you go, that's the first component. Likewise, the second component, partial y of x squared plus y squared, x is constant with respect to that partial differentiation, and you just get 2y. And lo and behold, there's the gradient of x squared plus y squared, just 2x comma 2y. All right. Let's get 3-dimensional. How about this? Nabla of x plus y squared plus z cubed. So I'll write it out. This is partial x of x plus y squared plus z cubed, partial y you guessed it, x plus y squared plus z cubed, comma, partial t. I am doing entirely too much writing for this problem. Once you understand what's going on, you would never bother to write this pretty much, because you can pretty much write down the answer with just a moment's thinking. What's the answer here? 1, yeah, 2y, 3z squared. Uh-oh.
Powering up, really.
What's that? No, I think it's just gentlemen in the back relaxing. It's fine.
Come on.
Now, so now you guys can calculate the gradient of a function, right? Say yes, yes. Yes. In theory, it really, folks, it's nothing more than differentiating a given function and with respect to the various variables involved in stringing them together in a vector. It's not really that big a deal. Read that as partial. So, okay. Now, there's lots of questions to ask here, right? Like, geometrically, what on earth is going on? What's the meaning geometrically of this gradient? How does that relate to the function, right? That's one question we might ask. There's more sort of existential questions like, can every force field be written as the gradient of a potential function? What's a potential function? What is a potential function? You just use the word potential function. You mentioned that until just now. This guy right here is called a potential. F is a potential function. Now, I'm going to put that in quotes because I'm using that in the sense of like calculus 3, which is reckless. We wouldn't call that a potential function. For us, potential functions are associated with potential energy, and that's got a wrong sign on it, SIGN. Let me get straight to the point before I could easily diverge into 3 weeks of calculus 3 here, and you should take calculus 3 and learn all the things I was just talking about in more detail. Let me get straight to the point here, though. For us, here's the definition. F is a conservative vector field or just a conservative force, if you like. On some subset U a subset of, I'm going to talk about it for Rn. Usually we're just interested in n equals 2 or n equals 3. This is, after all, classical mechanics. So F is a conservative force field on some subset of Rn. If there exists U, oh, that's a bad choice. I need to do something else for this letter here. Let's say D for like domain, okay? So if there exists U, which is a function from, say, D to the reals. Oh, sorry, this is a physics course. I'm not allowed to use that symbol. There exists. You guys know what English means. I'm safe for that. If there exists U from D to the reals, such that what? The force is equal to minus the gradient of that U. So a force is said to be conservative if you can realize that force is the gradient of a potential function. And by the way, we will soon have good evidence, good reason to call that potential function the potential energy function associated to the force. Okay? This minus sign is crucial to that. So potential energy function associated with that.
Are those V's or U's? Or
U's.
they're
All U's. There's U's in upside down triangles, otherwise known as nada. Okay. Now, is Is every force a conservative force? In fact, no. In fact, no, it's not. But some very interesting forces are, so it's not an FE discussion. But before I get into that, before I get into specific examples too much, I'll say we'll do one. Here's an example. Here's a good example. Suppose your force is equal to minus mg y hat. So I'll think two-dimensionally here for a second. Probably be three-dimensional. I don't think my next example will be f is equal to minus mg z hat. There you go. Variations on the theme. So my question is, that's equal to 0, comma, minus mg, two-dimensionally, right? So the question then is, if this is conservative, what you got to do? You got to find a u such that what? Partial u, partial x with a minus, right? Minus partial u, partial y gives you back that. So how do you undo differentiation? Integrate, right? In this context, yeah, partial integration. I mean, honestly, folks, you just guess. So a moment's thinking, and you can see that u of x, y, what will work here? Gosh, mgy apparently. Search your hearts, you'll find it's true, or better yet, just take a second and differentiate my answer. Put a minus on it, see if you get back. So if we take the gradient of mgy, where m and g are constants, what do we get? Zero mg, right? But that ever important minus sign makes it minus mg, right? The minus is not in the potential, it's in the definition of how the force connects to the potential energy function. And it's that minus that we don't bother with in Calc 3. At least most math books don't, I mean, for various reasons. So. How about the next one? Here we've got 0, 0, minus mg, so guess what? That suggests we should let u of x, y, z equals to mg, z. That will give you a potential energy function which reproduces 0, 0, minus mg.
Question.
No.
Why is, since we have a negative on this side, why is a negative not the original one? Like when we take a derivative.
What was that? Sorry. I know, it was very melodious. It filled my ear. Yeah.
I don't understand why we don't start with the negatives and begin with
I mean, you can put the minus on whatever you want. I was just differentiating. I was calculating the gradient of this expression, right? But that's not u. I mean, the gradient of minus mgy, that's my u, right? Well, see, that's this, right? Which is supposedly the force. But if you bring them, I mean, you leave the minus outside, I don't know. Where do you want to put the minus? I don't think I'm saying anything terribly interesting here.
I didn't know if it was supposed to be there anywhere, or would it just
What's the get?
the minus sign? I didn't even know if it was supposed to be anywhere in what we were doing.
Well, there has to be a minus here as the force relates to the potential energy for reasons which I will show you soon. So what does this show? This shows gravity, at least its approximation near the surface of the Earth, is what?
Conservative force.
Conservative force. Okay, so hey, that's an example we are very interested in. That's a conservative force, gravity, right? Now, in one dimension, I should actually also make a comment here. What's this animal look like in one dimension? How does this definition I just gave? How does it simplify in the one-dimensional context? It's probably worth just expanding on this definition in the one-dimensional case. N equals 1, your force is just replace a force which is a function of position x, right? And the gradient of u is just changed to du dx because there's only one independent variable. So there's no partial derivatives, there's only ordinary derivatives. And so the definition of a force being conservative in a one-dimensional context becomes F is equal to minus du dx for some u, which is just an honest to goodness function of one variable x. So for a one-dimensional case, the force is conservative if it's minus the derivative of some potential energy function. Let us look at an example. So the quintessential example I can think of, how about this? Hooke's law, F equals minus kx, right? That's a one-dimensional, there's a force which has an interesting, it depends on position, right? Force at position x is equal to minus kx. So to find the potential energy function, we would want that to be minus du dx. What does that make u equal to? Differentiate kx, I get k. Yeah,
Minus kx squared over 2.
almost right.
K.
Kx squared over 2, yes. We took your answer and multiplied by minus 1, so 1/2 kx squared. Now, you could also say plus some constant. And actually, if you think about it, previous two examples I gave also were not unique, because you could always add some vector of constants to this, like the gradient won't pick up on, if I'm differentiating, right? If I add 7 to this component, and if I add 3 to this component, and I add some function of x and y to this component, and do the same derivatives, I get back the same answer, right? So there's not a unique potential function for a given force field. You can always add at least constants, sometimes more. So is that, anyway, it's clear for this one. You see, if you differentiate that, you get kx, put a minus on it, you get minus kx. This is the potential energy function for this ring. Now, I'm using the words potential energy as if they mean something, but right now I've just done mathematics. I haven't justified why that has anything to do with the kinetic energy we were talking about last class, right? So let's get to it. Let's see why these are called potential energy functions. So as usual, we need a little bit more calculus 3, but not too much more. And certainly not the hard part of the course. So there's a theorem, the fundamental theorem of calculus for line integrals. What's the fundamental theorem of calculus for line integrals say? It says the following. It says that the line integral of the gradient of a function, let's say g, dot dr, over some curve. All right, and so the curve, I need some points, right? So the curve, it's an oriented curve. Since we're taking a line integral, it goes from somewhere, and from one place to another. Let's say it goes from point P to point Q. All right, so the line integral along some curve which goes from P to Q of the gradient of g is equal to g of the ending point minus g of the starting point of the curve. And there you go. That is the fundamental theorem of calculus for line integrals. So why does this have relevance to us? Well, last time we looked at the work energy theorem, right? So, let you guys catch up. Oh, here, an example. If I was integrating, say, 2x, 2y, dot dr, and suppose I've got some path which goes from 0, 0 over to the point 2, 3, right? Then this would be the integral. Hey, that's the gradient of what? X squared plus y squared, right? So all I gotta do is look at x squared plus y squared evaluated at the point 2, 3, minus x squared plus y squared evaluated at the point 0, 0. And fundamental theorem of calculus for line integral says that's it. That means what, 4 plus 9, 13. 13. Is there anything weird? So last time we talked about line integrals, right? And we talked about how you need to know the equations of motion for the path to set it up, right? The thing which might catch your eye about this example I just did is I just said it was a path from 0, 0 to 2, 3, right? I didn't tell you which path, right? So like, for example, if I had instead have taken this path, that path, for example, I would still have done a work of 13. I mean, the line integral would still be 13. I guess in order for that to be work, I would need another interpretation, right? What?
Can you change another color?
I'm
and
not
go
going to do
for-
another color.
It's
green.
more.
It's a wandering, meandering path whose exact location is not significant.
It cannot like. It cannot see.
For example. Whatever. All right. I give up. So obviously, if your force is conservative, or if the expression you're looking at can be written as the gradient of a function, that's really, really nice because it changes integration into evaluation, right? Which is essentially the fundamental theorem of calculus anyway, but okay, so getting back to why conservative force field, what's that have to do with this? So let's think about a case, all right? Let's think about the case that the net force is conservative, all right? Suppose the net force is conservative. All right, so what's that mean? That means we have two things. First of all, we have that the net force, this is what we talked about last time, is equal to the mass times the acceleration, right? And we learned last time that from this simple assumption flows the rather interesting result that the kinetic energy, the change in the kinetic energy was equal to the work done along some curve. Right? We did that last time. That was the work energy theorem. So the other thing we get now, point 2, we get that the force is equal to minus the gradient of the potential energy function. You might write U is equal to the potential energy function. I write that sometimes. The kinetic energy function, you guys remember, what was that? Yeah, 1/2 mv squared, right? Okay, so that's the input here. These are the two things we're assuming. We already dealt with one last time, so let's focus on 2 here today. So 2. Let's calculate the integral of f dot dr along some path c. What's that equal to? It's equal to, by assumption, minus the integral of the gradient of the potential energy function dot dr along the path c. Now, let me suppose that this curve C, it's some path which goes from, say, point 1 to point 2 or something, I don't know. Point 1, point 2. Here's my curve. So that goes from, say, at time 1 to time 2. We're looking at this motion. And we want to know what's the work done by this force, which is also conservative? How is that related to the potential energy for the force? Aha. So, you see what we have here? We have an opportunity to use the fundamental theorem of calculus for line integrals. Fundamental theorem of calculus for line integrals, which again, I would hope Dr. Wang will prove for you this semester. That would be minus u of P2 minus u of P1. I'm keeping the minus outside, right? So you might call that minus the change in the potential energy. So what this shows is that you can either think of the work for a conservative force field as being given by the change in the kinetic energy, or you can think of the work done by a conservative force over some duration as being minus the change in the potential energy. Put these two things together, what do we have? We have the change in kinetic energy is equal to minus the change in the potential energy. But let's write that more plainly. That says KE2 minus KE1 is equal to PE2 minus PE1 with a minus up front. Or simply, PE1 plus KE1 is equal to PE2 plus KE2. And that, right there, folks, is the main event. That's where it's at. Because that says what?
That the total energy is equal.
I'm sorry?
Conservation of energy, basically, right?
Right, yeah, so that is conservation of energy. So when the force is equal to minus the gradient of the potential, then we have u, basically u of x1 plus 1/2 m v1 squared is equal to u of x2 plus 1/2 m v2 squared. So, I mean, more specifically, this is conservation of mechanical energy. Later, you guys might go on to study electrical energy, or perhaps nuclear energy, or other things. And it turns out this concept of energy is rather ubiquitous. It's everywhere. And it's a far more fundamental notion than, say, forces. I mean, at some point or another, I should tell you about the four forces of physics. Like, what are the four forces of physics? What are the four forces? Yeah.
Gravity,
Gravity.
electromagnetic.
Electromagnetic.
and strong.
Weak and strong. That's right. So gravity, of course, has to do with this, right? Weak force. That's the least pleasant way to die. Radioactivity is weak force. Strong force. That's what glues the nucleons together, right? Like the strong force is mediated by these things called gluons. I'm not making that up. And that has to do with the story of quarks and how neutrons and protons hold together and all that stuff. What's the other one? Oh yeah, electromagnetic. We had a whole course about that. You guys take that next semester.
Yeah.
So those are the four forces. Now, but if you ask me, what is the strong force? Like, what's the formula for the force? Like F equals ma? I don't know. I mean, maybe people do talk about forces, but honestly, it's just kind of language. What we really talk about in those other theories of physics is energy. There's something called the Lagrangian. Lagrangian sort of captures the net way that the energy can work in the theory, and you study Lagrangians and how those govern particle content interactions. That's where physics is actually done. But anyway, so what I'm trying to tell you is this is actually the thing which generalizes Max's course. into courses that we don't offer here. But anyway, we did. Where it's at. Now, also, this will allow us to solve problems that we previously labored over solving with like stupid efficiency. Shall I show you one of those before we go on? Let me show you one of those. So, now, just before I go on, I should emphasize that this conservation, this changing kinetic energy being equal to the work done by the force, the net, it has to be the net force we're talking about, right? This is true even in a non-conservative case. Right, so this half of it is like generally true, as long as we're talking about net force. But when it's also conservative, then we get this wonderful conservation of kinetic energy, conservation of mechanical energy. Okay, so here's an example. You got this building, and I don't know, you've got some kind of sort of catapult. And I mean, it's a catapult, so you know what you have to put in it. Okay, and then you know you launch the cat at various at the same speed but different angles, right? And so then the question is, okay, so the cat hits the ground somewhere, right? And then you could ask what the speed was as it hit the ground for different angles, you know? And the answer is, what do you guys think the answer is? If you shot it at a high angle, it seems like it'd go faster, right? No, we shot at a lower angle. If you get somehow, like, I picture it quite right. You could launch it like down like that if you wanted to, or you could launch it up. Be the same. Now you say it's the same at any angle, but I think you could see how you might try to convince yourself it would be this different at different angles, right? Like, but you see the two competing effects. Is if you launch it up, then you know gravity is going to accelerate it back down, even though it does go up and kind of stop momentarily. It's got farther to fall, right? On the other hand, if you launch it downward, well, you're giving it that like downward speed, which gravity never takes away, right? It just adds to it. I mean, but here's how to solve this with energy conservation. So we have basically two events. Event 1 and event 2. An event is a time and a place. All right? Now, so at event 1, we can talk about the kinetic energy and the potential energy. I worked it out for you guys a little bit earlier today that the potential energy associated with gravity, right? So, what's the net force once the cat is launched? I mean, so we're just considering the motion. We're not considering the launching process as part of it, right? Just the projectile motion. The net force is what? Minus mg y hat, right? I just showed you, argued earlier, on this very board that is the gradient, minus the gradient of what? Mgy. So in other words, the potential energy at height y is mgy. That's potential energy due to gravity for the cat. Now, you know, there's a choice here. There's always an ambiguity, a freedom in defining the potential energy. This puts potential energy 0 where? I guess it depends on what y equals 0 is, right? Wherever y is equal to 0, the potential energy is 0. Where should I make y equal to 0? You're wrong. No, I mean, it doesn't matter. You got your choice. I mean, you can put y equals 0 wherever you want, but yeah, the ground is a good choice. I mean, telling you y equals 0 would be wrong. Would be kind of like me asking you what's your favorite color. Wrong. So, I mean, you can get that. So, it's a choice, you know, or it's a preference. It's probably boring that way. I didn't even watch the Oscars and kind of pull up this nonsense. It's either. So this would be height h, I usually would say. So let's set y equals 0. This is where potential energy is 0. let's just say potential energy 0 down there. Oops, sorry, I spread off the board. P equals 0. So event 1, finally getting to the point. What do you got? You've got mgh plus what? 1/2 m v naught squared. You see, it doesn't matter what angle you shoot this thing at. The speed is what fixes the kinetic energy. The kinetic energy is just based on speed, not on direction. So it's immaterial what angle you point it at there. Event 2, you've just got 1/2 m final velocity squared. Your potential energy is gone because you're down to where potential energy is defined to be 0. Energy is conserved, so you can just equate these two to actually find, relations between various things, like the initial speed and the final speed, for example. In fact, I can easily find that Vf is equal to, oh, you notice the m's cancel, and you just get 2gh plus v naught squared, square rooted. There's the final speed. Obviously independent of theta. Yep.
Isn't this the timeless equation?
Right. Yeah, and that was, I claimed that the timeless equation was conservation of energy before. Right? Right. I may have said that under my breath at some point earlier. Let's actually dig into that for a second here. I think we got 5 minutes. Should I take about 5 minutes? Oh, 4 minutes. I better hurry. So is the timeless equation conservation of energy? Timeless equation said what?
Vf squared is equal to v naught squared times 2ax, or 2a times x.
Yeah, v naught squared. And let's do it for gravity, okay? So minus 2g, let's do delta y. So I'm going to talk about gravity. So there's the timeless equation for vertical motion, right? The acceleration was minus g. So if we take this equation, multiply by m, divide by 2, let's see here, just to make it glaringly obvious what's going on, let's rewrite the change in y as the final y minus the initial y. I mean, why not? Sorry. Stand by that button. So 1/2 mv squared, 1/2 mvf squared plus mgyf is equal to 1/2 m v naught squared plus minus gives me plus mgy naught. As you can see, yes, in fact, the timeless equation was nothing but conservation of energy in disguise, which is why it's so powerful, by the way. One of the great advantages of the energy method, say over our force method, is energy is about scalars, right? It's about mg. It's, the potential function is a function. It's like a formula with x and y and z, perhaps, right? Kinetic energy, 1/2 mv squared. These are numbers. They're scalar functions. So it's a lot easier to work with these in some regard than it is to, say, solve Newton's equations. Now, you need the right tool for the right job, right? But for some problems, the right tool is Newton's equations and free body diagrams and all that, right? But there are other questions where the energy method is the way to go. So how do you know which one to do? Well, you look at which chapter I've assigned you the homework from, and if you're lazy, come on. You don't use logic. You just say if it's from chapter 6, it must be based on chapter 6 physics, right? I'm sorry, that really wasn't the answer you were hoping for, was it?
Test, which
Oh yeah, my test you don't know, I guess, but, well, I don't know. Maybe you do. I do seem to have some tendency to ask well-assigned questions, so. And Bailey being here is greatly increasing the likelihood it happens again, because it bothers her, and it makes me happy. Anyway, sorry if I taught you too much calc 3 today. I'll try to behave and do my physics exams next time. Thanks, guys.